simulate classically quantum physics on a classical device. What I want to do right now is to do the inverse operation, to implement tensor networks on quantum devices. And I will talk about this and show you why this is important. So let's start with a motivation. The colors are not rendering right, but okay. So what I want to do is I actually start by my motivation that I want to solve partial differential equations. And they come in various forms. For example, you want to model weather forecasting, you want to do a crash test simulation, maybe scatterometry, nanometrology, or in medical applications, like they come in any form possible. And the thing is, like, when you want to make them ever more precise, when you want to solve them ever more precise, you have to discretize your system even finer. For example, for weather forecast, you have to really go very deep because it's hard differential equation. And at some point, you come to a boundary where your classical device is not sufficient anymore, and you need a supercomputer, which is still not sufficient. And the idea is then that you want to implement differential equations on a quantum computer. And there's already a lot of people who have been trying to do that. There's a long list of papers, and they actually all are based on the first paper, mainly by using the Haro-Hasidim-Lloyd algorithm, which is a quantum algorithm for linear systems of equations, and which allows to invert a matrix in with an exponential advantage. And so most of the other algorithms are based on this first algorithm, but they all a lot of these algorithms are actually cheating on one point, and that is they're all using oracles. So they don't implement actually the differential equation, but at one point they say, okay, we don't know how to do this step, and so we use an oracle that is implementing this step automatically with time cost 1. So, and they write suppose A, which is the discretized differential operator of our differential equation, and we have an oracle OA that computes these entries. So this oracle actually implements this matrix on the quantum device, and also two controlled oracles, which are OX and OB, that implement the state, the initial state, and the forcing term. But the problem is these oracles don't exist, and we need to find a way how to actually implement these oracles. So let's talk a bit about computational complexity and why we actually think that that we can solve differential equation on a quantum computer in a faster way. And the first idea is that, like, we can store vectors on a quantum computer in a quantum way with an exponential advantage. Well, if I have a vector which has n elements on a classical device, on a classical computer, I need at least one element on my RAM to store it. But on a quantum device, I can use only a logarithmic number of qubits to store this vector. And this is, for example, done using amplitude encoding of the vector. But this is not the only thing that we want to do. We actually want to solve the PDE. And what do we need for that? For example, we need to be able to load the vector, and we need to be able to do matrix vector multiplication. And in a classical case, well, loading a vector, imagine you have a vector on paper and you have to load it on your computer. Well, you just type every number. It's a linear operation. And for the matrix vector multiplication, well, the fastest algorithm is some n to the power of 2.3, or like what is actually used is 2.7, but whatever. It's still something polynomial. So we know that usually solving PDEs is going to take a polynomial time using this naive approach. Well, how does it scale on a quantum device? Well, in the general case, still not very good, because if I give you the vector that I want to the initial state, if I give it to you in a classical way, because we live in a classical world, you still have to read every entry classically and put it on the quantum device. So this is still linear, so we have no advantage there. And for matrices, still it's n, like for a general matrix, this takes n squared because we first have to read every entry before we can actually load it into a quantum computer. So in this way, we have actually a problem when using quantum devices to solve differential equations. And we need, first of all, a classical order reduction in order to have a easy way to have like a faster way that the objects are stored in our classical world that then we can put on a quantum device. And for this, we have tensor networks, which are a classical tool that reduce the complexity of the algorithm from linear to logarithmic. So for and this is like for storing a vector, we using the tensor train formalism, we reduce from linear to logarithmic, and we can also, like loading the vector, we just need to count the elements and load them. And one could say, well, why don't we just use tensor network to solve the PDE in general? Well, yes, one can do that, but there's a caveat. We have this rank of the vector, and in general, this rank of the vector might explode and might actually reach the size of our system. So it might even become close to n, and then we cannot do that anymore. We lose the advantage on a classical device. But the good thing is that on a quantum computer, well, the rank of our vector, this vanishes because of how we have encoded the vector. So the entanglement helps us, and we don't have to count the rank of the vector when we want to solve the PDE. And the idea is, so we start from an easy state where from our classical state that we can load from our classical world and evolve the PDE on a quantum device. How does it look like if we talk of sets? Like here, we have the set of classically computable algorithms, and Q denotes the quantum algorithms. Well, we want to start from our classical phase where the ranks are very small, and then we go to the quantum phase, which is not reachable in a classical device. And the idea is that the ranks are of the order of the logarithm of the system size in the classical phase, and in the quantum realm, then these ranks explode exponentially and we cannot encode them anymore. So now let's look at how we want to encode tensor networks in quantum circuits. Well, the building blocks of tensor networks, you probably all know them. We have a vector, we have a matrix, we have an order 4 tensor, and we can just stack them together somehow, glue them together, and we get a tensor network. Now we want to transform this tensor network into a quantum circuit. This is not yet a quantum circuit, but we know what the building blocks of a quantum circuits are. We have cats, we have brass, which are like in a quantum circuit. This means we have a state preparation and a projective measurement into some specific state. Then we have unitary gates, which are just quantum gates, and we can also control these gates. And one important requirement is that all the lines, that we have a time ordering of our operations, and all the lines need to point from down to up for the quantum circuit, except for the control operation where we have a horizontal line. So the idea is, now we want to go from the upper diagram to the lower diagram, and we will do it only by diagrammatical identities. So first of all, let me introduce the delta tensor, which is also known as the copy tensor, and I denote it by a dot with as many legs as required. And this delta tensor is 1. The element is 1 if all the indices are the same. And for if there's only one index, then it's the all one vector. And so we can also find some identities for this delta tensor. The delta vector, well, this is equal to cat with a factor that we have to take out in order to normalize, because cats are normalized to have norm 1. And the delta tensor has a norm square root of d. And the second identity is that out of a line, we can introduce the delta, the order 2 delta, and out of this we can separate an order 3 delta and an order 1 delta. And we will need it later for our implementation. And the last identity that we can find is that delta with many legs can be decomposed in order 3 deltas. And if you look at this order 3 delta, well, I showed it actually also for the quantum circuit, and this is nothing else than a control operator. And this is how we will introduce, encode the delta tensor on a quantum circuit. Then the next building block that we need in order to transform a tensor network into a quantum circuit is that we need to transform the horizontal lines into something that we can encode on a quantum circuit, because this horizontal line, this contraction, is not implementable on a quantum circuit. Now here, these are two squares, but you can imagine that they even have that it's any kind of tensor, and it has also more legs as required. And the first step is that we introduce a delta order 2 delta tensor. Then we split up the delta 1 tensor and factor out the square root of d. And finally, do it also for the lower part. And we see now we have this state preparation here, and we have a projective measurement in the end with two controlled operations. Now we still have squares, and we don't like squares because, like, unitaries in the way I wrote them have rounded edges. So we need a way how we can round these edges. And this is done using unitary block encoding. And this is very simple. Any matrix can be block encoded on a bigger unitary in this way, that we just make the matrix bigger, add two legs, state preparation, and projective measurement. And we have this is how we encoded our matrix, with one condition, that we can actually only encode matrices that have the norm, like this largest singular value, equal to 1. And so we factor out the C, which needs to be at least as big as the norm of the matrix. And using these, well, we can start implementing tensor networks. And the first network that I want to implement is the tensor train operator, or matrix product operator. And this is like a series of contractions of matrices, or like order 3 and order 4 tensors. And the first thing that we're going to do, we replace the horizontal legs by the linear combination of unitaries in this way. So we have a lot of state preparation auxiliaries and projective measurements, and we have to factor out this R, which is a product of over the ranks of our tensor network. And the next step is that we're going to round the edges through the unitary block encoding, and by adding further auxiliaries and factoring out the C, which is a product of all the block encoding constants. So this is a very short, it's a low depth algorithm. This is like for if the physical dimension of the tensor train operator is 2, then this is an order, like it's a 4x4 unitary controlled here on one auxiliary and here by two other auxiliaries. So it's not it's not a long circuit, but there's a caveat, of course, that is the success probability. And to calculate the success probability, well, we have to look at the norm of the vector that we want to encode, or after we have encoded it. And how does this happen? Here we have a lot of projected measurements, and these decrease the norm of our vector, how we have encoded it. And the success probability is proportional to the norm of our quantum state after we have run the quantum circuit. And we can, using the tensor network formalism or the equation that I showed before, you can see, okay, it's the same as the classical tensor network applied on a test state with a factor of 1 over kappa squared. And what is this factor? Well, this factor is exactly this 1 over RC squared that we have here. This is the quantum circuit as we have synthesized it earlier. We applied on the vector, and this is the success probability of our algorithm. And this is the tensor network, and you have to think of this as a matrix product state. And this gives us the success probability. Now the caveat is that this R is actually, as I showed before, this is a product of all the ranks. So this the success probability of this algorithm decreases actually exponentially. Still, all that is not lost yet, because we can. I'm not showing them here, but there's some modifications that we can do to this algorithm by gauging the product matrix product operator in the beginning, because actually the C doesn't need to be greater than 1. It can also be smaller than 1, and maybe in some cases we can find a success probability that is not decreasing exponentially. But I did not do it yet. This is still current ongoing work. And the next tensor network that I want to implement is the canonical periodic decomposition. Canonical periodic decomposition is this kind of tensor network. It's a sum of a tensor product of matrices. And in the tensor network formalism, we can use this delta tensor to connect all the matrices in a sum. And the way we can implement this is by replacing this higher order delta by this sequence of controlled operations. And this implementation actually does not have the same drawback as the MPO implementation with the exponentially decreasing success probability, because this R is actually only the rank of the it's only one sum, and it's not like in the matrix product operator, which is a sum of sums. So it's exponential sum. However, with the canonical periodic decomposition, very often it's hard to compute on a classical side. So and now let's come to the final part. Well, actually, what are similar works that have been already done? There's two works that I know of. That one is block encoding of matrix product operators, which has been done in 2024. And this also shares this exponential decay in success probability in the general case. And there's another paper, which is tensor quantum programming, where they encode still the MPO. So this is only for matrix product operators, and they encode them with a high success probability. But the problem is that the error of the operator that they encode is actually scaling with the Frobenius norm of the operator, which, well, is very bad because it scales as a square root of the size of the system. So to sum up, what we have done is that we have presented a generalizable tensor network implementation. I have focused in this talk mainly on implementing operators, so tensor train operator and canonical periodic operator. But you can use this algorithm also to implement states and in the end to do a full network contraction. And this is our path forward to replace actually the oracle for the PDE solver, which still in the actual form is an oracle. And this gives a real construction. The only problem that this algorithm has is that in the general case, the success probability is exponentially decaying. And now the open question is, for which tensor networks and for which tensor network operators there is an efficient implementation possible. So thank you.
Yeah, the question. Don't you expect this R to be exponential in the system?
In this case,
yes.
Well, this R, I mean, this only depends on, I mean, it depends on what
exponential is going to be exponential.
It depends on what you actually want to encode. The thing is, like, this R can be 2, it can be 1. And if you think, for example, what this is, for example, a sum of Pauli's. This is the same thing. It's actually,
if you could do this for a genetic NPO.
If you want to transform an NPO into a then this is exponential. Yeah, it's difficult to compare. But if you have something that you can transform into a canonical periodic decomposition with a low rank, then you can implement. And this is usually what is being done with the sum of Pauli's approach, which is a sum of tensor product of Pauli matrices. And also finding the exact rank of the canonical periodic decomposition is NP hard and NP hard task in general. So this is, if you know a low rank decomposition, then you can implement.
Any other?
Yeah. What?
You say exactly what quantum computer would improve in?
Well, that you in like for the weather forecasting, you need a very fine discretization, and using a quantum computer, if it gives you an exponential advantage, and you would be able to discretize your grid even finer and theoretically exponentially finer. The only thing that you have to consider, like that, is that your PDE, like the way I presented it, is that you start from a low rank like tensor network state, and your PDE has to be such that it increases the rank of your tensor network. And then this is the advantage that you have, that you start from a low rank tensor network, and in the simulation of the PDE it becomes more complex. And for the weather forecasting, since it's a nonlinear PDE, then you would actually expect that there's fractals or whatever weird things happening that actually make the rank of your tensor network explode. This is okay. This is a question: is how do you read out the solution? And this is another topic. Like this is like all about quantum, like solving the PDE, and then you cannot read out the whole vector in the end, but you can calculate some quantities of interest, and so some moments. So you're a bit more limited, but the idea is that if you can make the like that there are maybe some interesting quantities of interest that you cannot calculate otherwise. So you have to tweak it so that you to actually get an advantage.
I have a question. I don't know much about it, but what do we take actually?
What these shapes represent?
Yeah.
Like I mean,
The triangle.
yeah, I mean. So this is for the quantum circuit. So this is a catch. So this is a vector, and it's like a quantum state, and this is the dual. So for a quantum circuit simulation, this would mean that you first prepare your state in this vector, and then this is a measurement, and you measure your state, and the computation is successful only if you measure the correct state. So if you measure a different state, then you have to throw your computation away. And this is usually an auxiliary, and in the end, you want it to be zero.
And so the control?
The control is it's a control operation, so that you apply, like usually it's combined with a quantum gate. So this control acts only on a specific state of the auxiliary, and on this state it applies this quantum gate, and then on another state it applies a different quantum gate. So it's like this, like if you leave out this line, this is a unitary, and if you put this line, then it's a sum of unitaries, kind of, or it's like a vector of unitaries, let's say, and each unitary is then implemented on a different auxiliary state.
So since you now have a representation of Lorentz curves, Lorentz tensors, is it the next step or the next wish to do Lorentz decomposition of computers, or is it system like that?
I mean, the idea is that we want like the circuits, the algorithms, the classical algorithms that use tensor networks that have the problem of exploding one dimensions, that you transfer them on a quantum device, and then they're the one dimension, you don't care about it because they're kind of given for free. At least for, I mean, if you encode it in the right way. Yeah, but I mean, a quantum and I first need to solve the problem with the exponential also have. And my question is also actually if there's a no-go, like if it is even possible in general, because Frank earlier said that like if you do full network contraction, then this can be
Lorentz decomposition is already